Alright, so this second video is going to focus on energy changes associated with spectrums. We're going to be focusing specifically on hydrogen since that is the one element that the Bohr model successfully fulfills. In terms of spectrums, we're going to be looking more at emission spectrums, but to kind of put that in context with the visible spectrum of light, a continuous spectrum would contain all of the potential colors that you would expect to see, all the potential wavelengths for visible light, while the line spectrum just shows the energies or the wavelengths of light associated with energies that are allowed for that specific element. So the wavelengths that we're seeing for the emission line spectrum for hydrogen, those are the potential energy changes that can occur for hydrogen's electron. So the Bohr model was able to use a lot of theoretical data to come up with an equation to calculate the energies associated with those potential energy levels. Remember, the Bohr model is only allowing you to move in circular orbits. So we have that constant, the negative 2.178 times 10 to the negative 18th joules. And then we have a z squared over n squared. N is referring to the orbit in which the electrons are in, while z is referring to the charge of the nucleus. For hydrogen, that would be 1. And we can determine energy changes by using that equation to take the difference between the electrons at a final E level and subtracting away the energy associated with the electrons at an initial E, or an initial orbit N. So I have a couple pictures here. The one on the right is showing you the emission line spectrum for hydrogen, and it's showing you the colors, the wavelengths of light that you would expect to see if you had an electron for hydrogen move between an N of 5 and an N of 2. The green shows what would happen if it moved between an N of 4 and an N of 2. Then the red shows what would happen if you moved between an N of 3 and an N of 2. The line graph on the left side of this picture is showing us what it would look like as you increase in your N's. You're having more and more energy being associated with them, but they are getting closer and closer together. And so the arrows are showing the movement from a higher energy level to a lower energy level. And that's similar to what we'd expect to see with the absorption of energy with our flame test. And then what you're seeing there with the arrows is the emission of the wavelengths of light that we see when the electrons are falling back down to their ground state. So what we're going to do, and you're going to have a problem very similar to this on your homework, you're going to just do a couple different energy levels. We're going to calculate the wavelength of light emitted when hydrogen undergoes a transition from n equals 5 to n equals 3. And then we're going to set up a graph similar to the one that I just last discussed, showing the transitions on an energy level diagram. So we talked about how delta E is the difference between the final and initial energies, and we have a constant that E is associated with. Because it is for both E's, we can actually pull it out and just look at the difference between the n squared for the final and the n squared for the initial. That 1 is coming from the z value. Since that's 1 squared, both would have a value of 1 for hydrogen. So since we are ending at 3 and we are starting at 5, n final would be 3, and initial would be 5. And now we just need to do the mathematics. This is just simple algebra at this point. You're going to divide out your square roots and then multiply by your constant. I don't really worry too much about sig figs at this point. The 5 and the 3 are exact quantities. So the constant, the 2.178, is pretty much what's going to determine our energy change. So when I go through and do the math, I got that the E was negative 1.55. You could have had another sig fig if you wanted. But honestly, with this, I think as long as you keep 3, you should be good to go. Why that energy value is important: if we have that energy, we know that we can relate energy to a wavelength, and so we can calculate the wavelength for that particular energy change. So if we use our delta E equals hc over lambda, we get that the wavelength would equal Planck's constant times the speed of light over that change in energy. Again, not really any sig figs with this one. I think you could have gone with 3 or 4. The joules cancel, the seconds cancel, and when we multiply and divide through, we get that the wavelength would be 1.283 times 10 to the negative 6, or 12.83 nanometers. So that would not be one that we could actually see because that's below the visible spectrum. We can show this with an energy level diagram. We want to go from 5 to 3. So if you take that energy level diagram we saw before, we would want to start it at 5, end it at 3. We obviously would not see that color of blue, but just showing you an arrow as to how that the energy would be moving. We could also use something like this. We could use a wavelength or a frequency to determine what quantum level the electron either started at or what level it ended at. This time I'm giving you frequency. We can use frequency to find the total energy that would be associated with it. We haven't seen frequency a whole lot since the beginning of this unit. Delta E is also equal to Planck's constant times that frequency value. So if we know the frequency and we know Planck's constant, we should be able to find the energy change associated, which was 7.560 times 10 to the negative 20th. We're told light is emitted, so that delta E would be going through a exothermic change, and so that's why the sign is negative. If it had absorbed light, it would be positive. So we have our delta E, and we know we got to an N of 4, so we can go ahead and substitute in for N final an N value of 4. And at this point, again, it's algebra. We have our delta E, we have our constant, and we're solving for N initial. So at this point, I just went ahead and simplified the fractions as best as I could. I'm going to distribute through. Actually, I think what I did instead of distributing, I divided both sides by the negative 2.178. That gave me a constant on the left side of my equation. I still had the 0.0625 and the minus 1 over x squared on the right side. I could subtract the 0.0625 from both sides, and that leaves me with negative 1 over x squared equals that constant. The inverse would be x squared is around 35.98, and I'm guessing you're probably seeing at this point that the square root of x would be around 6. So the quantum level at which the electron began at would be closer to 6. Okay, and that was the end of the second video. Pretty short and sweet.